Welcome to our talk. We're going to be covering an intriguing topic, whether you can write an assertion to detect a narrow glitch or spike on a sensitive analog line. This work arose from a paper we wrote last year, a UVM test bench for a programmable low dropout voltage regulator, or LDO. And this slide shows a possible scenario where a bias generator supplies bias to one or more LDOs on the chip. Due to the length of the metal lines and the small feature sizes we see today, even though we do a careful job of shielding and routing, it's possible for a noisy aggressor signal on an unrelated line to be coupled electromagnetically through this unwanted capacitance. And the result is you've got a spike. It could affect the LDO itself, or even worse, the circuits downstream that depend on its regulated voltage. This scenario could also arise from EMI noise, or perhaps to rebooting or reprogram the LDO to use a different bandgap voltage reference. Here's the simplified model we're using for our bias line VBN. In the original LDO, we had a two-stage CMOS op-amp, about 9 transistors. Here we're simplifying it to just this one transistor, and this is the NMOS bias voltage pin on the op-amp. During the LDO's power down mode, this CMOS transmission gate is wide open and no voltage is applied. But as soon as we resume normal power, this transmission gate closes and VBN will rise exponentially due to the parasitic resistance and capacitance of this metal line. And our spec calls for a valid range of 700 millivolts plus or minus 50. The problem, though, is that a narrow spike or glitch arising from the scenarios we just discussed may go undetected by an unaided system verilog or PSL assertion. So let's give this a try. Let's write a rather simplistic assertion which asserts an unnamed property, namely that the value of VBN should remain between 650 and 750 millivolts. Notice there's no explicit clocking shown here. We're using a default clocking scheme where the value of VBN is evaluated at rising edges of this 1 nanosecond test bench clock. As the LRM states, and as Ben Cohen's SVA handbook emphasizes, a concurrent association evaluates its signals only at those clock ticks. So, with a narrow spike like this falling smack between rising clock edges, the assertion VBN value check will miss the spike entirely, and worse, it'll pass blindly. So can we do better? Well, our first thought may be to increase the clock rate and evaluate VBN more often. So here we succeed in detecting this first spike. It happens to span a rising edge, but there's still no guarantee that subsequent spikes, due to their narrow range or their position between clock edges, may go undetected completely. And so the real problem is that we're trying to deal with a real valued analog signal VBN, but only using discrete time values. So let's examine the underlying paradigm. Here's the traditional paradigm that we've been following to this point for this arbitrary analog waveform, piecewise continuous waveform. We're basically representing it as a mathematical time sequence of pairs, time value pairs. We can sacrifice simulation speed for better accuracy by using more points, but there's still a finite time interval between two successive points, and they can still conceal a narrow glitch, and our unaided assertion will still pass. Maybe what we need to do is depart from the point-based paradigm entirely. So here is another paradigm which relies more on continuous time monitoring. And this is embodied in Scientific Analog's X model simulation package. I'm going to try to focus on the concepts behind X model, not so much as the tool features, but I'll just say that X model is a plug-in extension to commercial logic simulators like Excellium or QuestaSim or VCS. Instead of WReal, it has a type we call XReal. And any segment of this general analog waveform can be represented by an analytic function, like this one here. If you dig up your old college calculus text, you'll recall that an analog function is well behaved in the sense that it's easy to differentiate and integrate and can be represented as some kind of power series. The form of power series we're using here has an exponential factor, and the reason we pick that is because it has a Laplace transform of the simple form 1 over s plus a sub I. So over any given interval, we can represent the analog waveform by this analytic function or expression. Then here we change to a decaying exponential. Just one event is required, and now we have a new analytic function. This one is even simpler, and its power series can be represented by the parameter values m sub I equal to 0, c sub I equal to 1, and a sub I equal to 1 over tau 2. So this x real variable is really a structure that keeps track of these parameters. And as you can see, very, very few events are required, only when we change from one analytic expression to the next. To drive that point home, let's look at slide 8 before we go further with our solution. And here we're using Scientific Analog's X-Wave utility. It's a waveform viewer that can render not only ordinary bit and real types, but also X-real types directly. And we've got event markers turned on, but simply by pressing the M key. So this drives home the point that this entire analytic expression only required one event. Even the spike, if we look at it, zoom in this inset, it may require a few terms in the power series, but still only one event. So it allows a simulator like Excellium to perform analog assertions and do continuous time monitoring, still running at close to normal logic simulation speeds. Okay, that brings us to our solution of this problem. Because these analytic functions can easily be differentiated and integrated, they allow many waveform-specific measurements. They can detect, the X model measurement primitives can detect threshold crossings, or do time integration, or determine slew rates very easily. The two X model library elements we want to use here, however, are measure max and measure min. As their names imply, they determine peaks and valleys over some user-defined time interval. To use them, we simply instantiate them in our test bench using ordinary system Verilog instantiation syntax. Notice they take the same input signal the X real variable VBN and the output real valued measurements, a max and a min. That is the max and min over a user specified time window. And how do we determine that window? Well, the primitives have from and to pins. And so we feed in possibly two distinct triggering signals, call them tick and tock. Here I'm using a shortcut and I'm using the same signal tick. The primitive is smart enough to realize that the time window is defined by successive transitions on tick. It's actually the X-bit version of tick. And it's very similar to system Verilog bit type, except it models the timing of transitions more accurately. So we've added these two measuring primitives to our test bench. And we can now use them over a given time window. The measure max primitive will examine the time domain expression of X real variable VBN and compute the first derivative. And so the first derivative will cross zero at the point of this maximum, and it'll have to be a falling zero crossing. And by keeping track of all of those, measure max determines the highest peak within this from to interval. And so we can now create a more robust Boolean condition for our assertion. We'll use the system Verilog let statement to describe that. It's a kind of a text macro. Notice we're not using values of VBN directly, but only these real valued measurements coming out of our primitives. Is the highest peak less than 750 millivolts? Is the lowest peak greater than or equal to 650 millivolts? If so, our condition VBN valid is true. Here's a simulation run using Cadence SimVision. Now, we can't display an X real variable, at least not directly in SimVision, but not to worry. We just instantiate a simple X real to real converter, one of the library elements. And so what you're seeing here is actually the real conversion of VBN. And as soon as we leave the power down mode and enter resume power state, VBN begins to rise. At the cursor, it has just entered its valid range, 650 to 750 millivolts. And thereafter, we can measure using our trigger signal tick, shown in gray here, between every two successive transitions, as indicated by this yellow shaded time window. At the end of that window, we'll get a definite max value and min value. For example, the VBN max might be, 655 millivolts. The point is that these are the true measured extrema. So here's our assertion. Using this VBN valid condition, we can detect narrow spikes. Let's do it this way. Let's create a system Verilog sequence to define the window of time over which we want the checking to take place. So in our sequence, we wait till VBN valid has gone true. VBN has risen, in other words, into its valid range, stays there for one or more clock cycles, and we'll continue to check our assertion until we again change state. The LDO leaves resume and re-enters power down. So this window sequence delimits the checking interval. Now we can define a name property. We want to give it some logical antecedent so that we're not creating lots of unnecessary threads. But the main thrust of this property is that we're asserting that VBN valid should be true throughout the time window defined by our sequence. So here is our assertion. We're asserting the name property we've just defined here. We're giving this a new name, VBN stable check, and it has an action block. We'll print this message if the assertion passes, this message if it fails, and we'll also increment the number of failures. So there is our new assertion, based not on the discrete time values of VBN, but these continuous time measurements of maxima and minima. So here we're zooming in on the same simulation run. We're focusing more on the spikes. And to generate those spikes, we first assert this yellow signal called INJ, short for inject. As long as it's high, we will be injecting spikes using this binary green spike trig signal. Every time it transitions high, bingo, we generate an upward spike. Every time it falls, we generate a downward spike. And at the bottom of this SimVision waveform, you can see that soon after we entered the valid range defined by these blue horizontal lines, the assertion VBN stable check went active. And it remains active until the first spike causes a failure, shown in red, and then the subsequent downward spike causes another failure, shown in red, and so on. Total of 12 spikes, and all were caught by our test bench. One slide on generating these spikes. We're not doing this in a lab environment, so we don't have access to a nice arbitrary waveform generator to create noise. We need a software means of injecting spikes. So we're going to use procedural code, basically a while loop. As long as the inject signal remains high, we'll use $u random range to compute a random delay. We're generating one between 5 and 10 nanoseconds of delay. You can adjust these parameters to control the density and number of random spikes that you want. And then we're using this random delay to generate the next edge of spike trig. So there is a random delay between these two edges of spike trig. Spike trig is an ordinary bit signal. We want to convert that to X bit in order to feed it into another X model element called transition, very similar to Verilog AMS transition filter. It converts a binary transition into an analog one, then feeds it into a series RC circuit. And so we get a narrow spike injected into our VBN line. These resistors and capacitors are chosen for very narrow spikes. Meanwhile, measure max and measure min are still continuously monitoring the VBN line. And so in conclusion, using this paradigm, we did succeed in detecting very, very narrow spikes, just a few picoseconds wide, even those falling between assertion clock edges. We did it by aiding the assertions with these X model primitives, measure max, measure min, and we did so without the need to sample values more frequently. So our test bench caught every spike on the bias line VBN with little or no speed penalty. Thank you for your attention.